Okay, so what did we do yesterday? You guys looked at videos, right? And the videos were talking about what click everything close, what the representations are of linear equations in 3 dimensions. And what were they? A linear equation graphed in the variables x, y, and z. What does that graph look like? It's a plane. Yeah, good. It's a plane in space. It's not a line in a plane. It's a plane in space, right? Okay. So what about then, what would be the possible, and let's remind ourselves about that, right? So if we look at the XYZ space, right, this is kind of unique. If we want to create an orthogonal space, which means all of the axes are at right angles to each other, in a 2-dimensional plane, we only have room for 2 axes, like the X plane and the Y plane. Those meet at a right angle, right? But if I add an extra dimension, if I add 3 dimensions, now I've got room for 3 axes. I could also have the z-axis extending out of the board, and we can see here that all 3 of these are perpendicular to the other 2, right? Each one is perpendicular to the other 2. So in math, we'd call that an orthogonal space. That's a place where all the axes are perpendicular to each other. Now, do we have room for a 4th axis in 3 dimensions? We don't. Any other axis I drew could not be perpendicular to all 3 of those in 3 dimensions. Okay, that's what distinguishes a 4-dimensional space from a 3-dimensional space. A 4-dimensional space would just be a physical space where there would be room for another orthogonal axis. But how could you do that, right? I mean, we can't visualize it because there isn't room in our 3-dimensional space for that. But a 4-dimensional creature living in a 4-dimensional universe would say, oh yeah, it's obvious. It's just right there. And they would have room for one, which we don't, okay? We'll kind of, not today, but next week, we'll kind of talk about what that might imply in 4 dimensions, okay, but not today. So if we have an ordered triple then, if we want to locate a point in 3-dimensional space, we need 3 coordinates, not just 2, because I have 3 axes now. So if I have the ordered triple 2, 3, 4, that's an x coordinate of 2, y coordinate of 3, z coordinate of 4. That would mean starting at the origin, I'm going to go right 2, up 3, and out of the board by 4 to some point in space. Okay, everybody good with that? Just a quick review from yesterday. So a linear system then would be, and if we want to graph a different plane, like x plus y plus z equals 1, well, we could use the technique, you guys saw this yesterday, we could find the x-intercept by setting y and z equal to 0, and we could find the y-intercept by setting z and x equal to 0, and so on. And we could create 3 points, and I'm going to let you take a stab at this here. It takes 2 points to define a line, right? How many points does it take to define a unique plane? 3. 3 non-collinear points, right? So if I created 3 points corresponding to all 3 of the intercepts in space of this linear equation in 3 variables, well, I could just connect all 3 of those with a single plane, and that would be the graph of that linear equation in 3 space. Okay? That kind of making sense a little bit? Okay? All right, so then what if we had 3 equations in 3 variables? That would just be 3 planes. Now, what were the different possible outcomes when we graphed? Well, let's look at this vocabulary real quick. Remember really we talked about this with 2x2 systems. A consistent system has 1 or more solution. Inconsistent means no solutions. Dependent means all equations are the same. And independent mean different equations. The graphs are not all the same. They're all different, right? So we had a bunch of different possibilities there, right? If a system is consistent, that means it could intersect at a single point, it could intersect at a line, or it could intersect at one plane. Make sense? In the top 2 cases, those are independent systems because all 3 planes are different. This is a dependent system because all 3 planes are the same. They overlap completely, okay? And then we could also have instances where we have 3 planes that never all intersect in the same place, and we'd call those inconsistent systems. Could have 3 parallel planes. We could have 2 parallel planes and another plane that cuts through each of them separately. Or we could have 3 planes that never all intersect at the same place. This case, they just form like a triangular tube you could look down, right? Okay, give me thumbs on that. Does that all make sense? All right, so then next step is, how can we solve these things algebraically? Okay. Solving these algebraically is very similar to what we did with 2x2 systems, only we have an additional step in here. We're always going to use the elimination method, first of all. We don't ever want to use substitution. We always want to use elimination. And that's why, well, because it's easier, but also because as you get further and further along into bigger systems, 4x4, 5x5, you definitely want to use matrix methods, which I'll show you guys, not today, but those all rely on writing the equations in standard form. So when you're solving linear systems, standard form is the best way to go. So we got to write standard form for 3 variables is just x term first plus y term plus z term equals constant, right? So the way we do this is we're going to try to reduce this down to a 2x2 system that we could solve by eliminating the same variable. By eliminating the same variable from 2 pairs of equations. And then when we solve that 2x2 system, we'll know the identities or the values of 2 of the variables. Then we could plug that into any of the original equations to find the third. Okay? So look at this system here, and can you guys tell me now, can you find, what would be the easiest variable to eliminate from 2 different pairs of equations? Y would be, wouldn't it, right? So we could eliminate y from the top 2 equations by simply leaving the top equation alone and multiplying the second one by 6. Everybody agree? Okay. That would give me my top equation just stays 2x minus 6y plus 9z equals negative 8. Middle one, if we multiply by 6, we get 30x plus 6y plus 12z equals 60. And when we add those up to eliminate the y's, we get the result 32x plus 21z equals 52, right? Okay, now we need to pick another pair of 2 different equations and eliminate the same variable, and you guys already picked y, so how about if we pick the bottom 2? If we pick the bottom 2, we would multiply, leave this one alone, and multiply this one by, bottom one by negative 1. Giving us 5x plus y plus 2z equals 10, and negative 3x minus y plus 8z equals 28. Add those up. Again, the y's cancel. And now I get, what, 2x plus 10z equals 38. Agreed? Okay, let's combine that with this other equation, stick that over here, and we get 32x plus 21z equals 52. Okay, now which of those 2 variables, x or z, would we, now we got a 2x2 system, right? This is like going back to the previous section, and just, that's easy to solve. We would solve by elimination. Which variable would we eliminate, x or z? X, for sure. Multiply the top equation by
16.
By 16?
Yeah. No.
They have to cancel. Negative 16.
Oh. I was crossing kilograms.
Okay. So we get negative 32x minus 160z equals negative 300 plus, so what's that going to be? We're going to get 480. So we're going to get 80 minus, so that's negative 608, yeah.
Yeah. My God. Here, give me a calculator.
Okay, good?
Yeah.
Good. And sure enough, we get the x's to cancel. And that gives us, what, negative 139 z equals negative 556. Okay, what would I do to solve for z? And that's going to give me what? 4.
Calculator.
There you go. Okay. So we know z is 4. How would we find x?
Plug it in.
There you go. I'm just going to plug it back in. I'm probably going to plug it in right there. Okay, and that's going to give me 2 times, oh, that was z, sorry, 2 times x plus 10 times 4 equals 38. Okay, so that gives me what? 2x equals negative 2. So what's x equal? Negative 1. Okay, there's 2 of our 3 variables. Now what? Yeah, probably the middle one, I guess. Seems like the easiest. All right, so we'll just take this guy right here and let's take that guy and just go down here. And we get 5 times negative 1 plus y plus 2 times 4 equals 10. Solve for y.
Yeah.
7? Yeah. Right, negative 5 plus 8 would be 3. Subtract 3 from both sides. And we get y equals, that looks like a z, doesn't it?
A little bit.
Y equals 7. And so now we've got our ordered triple, negative 1, 7, 4. So this intersects at a single point in space, and that's where it intersects. How could we check our solution? Plug it back into which equation?
Same one we used.
If I want to check the solution of the system,
The smallest equation.
which equation do I plug it into? All of them. All of them. I have to plug it into all of them. To be a solution of the system, it has to be a simultaneous solution of all the equations in the system. So it has to work in all 3 to be a solution of the system. Okay? All right, let's try another one. This one is easier. We've already got some coefficients are 0, and so it makes this one quite a bit shorter.
The top and the bottom. No, the top and the...
Well, which variable would we want to, okay, top and the bottom, you're right. Which variable do we want to eliminate from the top and the bottom?
Z.
Actually, I'll tell you what, let's do it differently. How about if we do the middle 2? What variable do, the bottom 2, not middle 2, there aren't middle 2. Which variable could we eliminate from the bottom 2? Z. How come? Because look, the first equation already only has x's and y's, only has 2 variables, right? So it'd be easy for me to combine the other 2 equations in a way to eliminate the z's and also just get x's and y's, right? All I'm trying to do is just condense this down to a 2-by-2 system. So I already have one equation in 2 variables. Let's use the other 2 equations to get the same 2 variables, right? So we could multiply this guy, leave this one alone, right? Multiply this one by 2, and we get y minus 2z equals 3. Multiply the bottom one by 2 and we get 2x minus 8y plus 2z equals 8, right?
Yeah.
Add those up. The z's cancel, and I get the equation 2x minus 7y equals 11, right? Okay, there's an equation in x and y. Where am I getting my other equation in x and y? Top one. I already have it. It's right there. So that guy's just going to go down. That's a bad arrow. How am I going to do this? This guy's going to go like this. This guy we're going to drag over into this system, and we get negative 3x minus y equals negative 5. Now I can just go to town on this 2 by 2 system. Which variable should I eliminate?
The y.
The y, absolutely. We'll leave the top equation alone. Okay, what am I going to do to the bottom equation?
By positive 7. I mean negative 7, just kidding.
By negative 7. Good. Okay. So that's going to give me 21x plus 7y equals 35. Add those up. The y's cancel. I get 23x equals 46. What's x? 2. So I'll take that value and plug it into, how about, doesn't matter, bottom one I guess, I'll just plug it in right there. And I get negative 3 times 2 minus y equals negative 5. So what is that? Negative y equals 1. So y equals negative 1. And then all I need to do is find z. Which equation should I use? Yeah, middle one, absolutely, right? Just use the middle one. We'll use this guy. Oops, wrong color. We'll use this guy, and we get y minus 2 times z.
Wait, when you put
Oops, you're right.
Yeah.
Y, we know y.
Yeah.
So negative 1, or yeah, negative 1 minus 2z equals 3. So negative 2z equals 4. So what's z? And we got it. We got our ordered triple, right? Make sense? Okay. So we combine all three of these in the ordered triple: 2, negative 1, negative 2. Okay? All right, let's look at a weird one. Okay, what about this guy?
I say the bottom 2.
Bottom 2 look pretty easy, right? So what are we going to eliminate?
The y.
Y's. And we'll bottom 2 and then maybe top and bottom?
Yeah.
Make sense? Okay. So let's take the bottom 2.
You know,
We can just leave these alone, right?
oh yeah, you're right.
Add those up. Y's cancel. We get the equation x plus 3z equals 14. And we could just multiply the bottom one by 5 and leave the top one alone, right? So we get what? Negative 5x minus 5y plus 20z equals 20. So if I add those up, what happens? The y's cancel, but what else happens?
All of them.
All of them cancel. So what do I get on the left side of my equation? 0 equals 25.
That can't happen.
Yeah, so what do you think's going on here?
Um,
No solutions. Yeah, there are no solutions. So that means that this is an inconsistent system, right? There are no solutions. Okay? All right, let's look at another weird one. Oh, and by the way then, so how would I enter this? What would I do?
I don't know.
Which one of those three choices would be the correct one? C. It'd be C, wouldn't it? That's the one we just did.
Oh,
Okay,
yeah.
yeah.
I'll have to go back and call.
Okay, so what about this one? Here, let's do this. I'm going to take a picture of this, and we'll do it on, we need to do some work. So we'll do this on a separate page. Oh, there, never mind. It's down here already. Okay. So take a look at that. What would be a good variable to eliminate?
The top and the bottom. I say.
You just multiply 4 by the top.
There you go. Good. And then top and bottom, right? That'd be good. Okay, so top 1 by 4. Bottom one we just leave alone, right? Okay. So 3x, I'm sorry, 12x minus 16y plus 4z equals 0. Bottom one, negative 12x plus 16y minus 4z equals 0.
If we know x plus y equals 0, wouldn't we just be able to set them to 0?
No.
No.
No, because x could be 5 and y could be negative 5. X could be 10, y could be, you see what I'm saying? There's an infinite number of possibilities that would add 0. If I add all those up, what happens?
You get 0.
I get 0 equals 0.
Yeah, that's true.
Okay, so what does that tell you about the top plane and the bottom plane?
That they're the same.
They're the same. They're the same plane, right? Okay, but the middle plane might be different. In fact, it is different,
Yeah.
right? If I added that, I'm not gonna get stuff canceling if I add the first two up, for example, right? So what if I tried to eliminate x from the first two? Okay, I could leave the top one alone. And the bottom one I would just multiply by negative 3. Isn't that what we were trying to get rid of was x? Oh, we're trying to get rid of z's, weren't we? Yeah. Okay, we can't get rid of z there, so we'll get rid of x's. Get rid of x's. So we'll multiply this one by negative 3. That's going to give me negative 3x minus 3y equals 0. I add those up, and the x's cancel, but I end up with the equation negative 7y plus z equals 0. Okay? So when I intersect these two planes, I get the line negative 7y plus z equals 0 in the yz plane. Okay? So what's that telling me? That tells me that z is equal to 7y. Okay, how am I going to make sense of this? So what do you think the right answer is then? A, B, or C?
I say B.
It's going to be B, isn't it?
Yeah.
Right? Because I did not get a single ordered triple, but I also didn't get an untrue statement, right? I didn't get a false statement. So it definitely is B. So I don't want to go do too much with this. How do we identify what the solution is? How is it infinitely many solutions? Because it doesn't just mean it could be any point in space would work to solve this system. It's an infinite number of points, but they have a pattern, right? They have a pattern, and this is the pattern. Z is always equal to 7y, and we know something else. Look at this one right here. This tells us that y is equal to negative x, right? Let's do it a different way. Rather than solve this for z, I'm going to solve it for y. Y equals 1/7 z. Everybody agree?
Yeah.
If I solve that, I get y equals 1/7 z, and I also know that x equals negative y. Okay? So how could I write this answer then? Well, one way I could do it is I could say if z is any real number, could be anything, what is y going to be in terms of z? Well, y is going to be 1/7 z. So I would have and what is x? X is negative y, so it's going to be the opposite of that. It's negative 1/7 z. And that would be the ordered triple. It's the solution set of all of those ordered triples where z could be absolutely anything. Did you finish it?
Yeah.
Okay, perfect. And you'll just submit your work?
Yeah.
Awesome. Is that my Chromebook?
No.
Oh, okay. Make sense? Okay. So what does that mean? Well, it means we're going to get this weird plane, and the plane looks like, if I were to graph the line in the YZ plane, it would just look like y equals 1/7 z, which is just going to be some line in the YZ plane. Or actually let's do it in the XY plane. We're used to that. In the XY plane, we get the equation y equals negative x or x equals negative y. Well, that's pretty easy to graph, right? That just looks like a line with a slope of -1 through the origin, right? So here's my line in the XY plane. Z could be any real number though, right? So for example, the point x equals 1, y equals -1 is going to be a point on our line, but z could be 10, it could be 1,000,000,000, it could be pi, it could be -7. So what's that mean that in 3 dimensions our solution is going to look like? No, what's it going to be? And what's the plane going to be doing? How is it oriented? This is really tricky, but see if a light comes on here. Well, no, it's going to be a plane, but if the x and y coordinates are 1 and -1 respectively, z could be 7, it could be 3, it could be 20. So those are all parts of a plane that just cuts into the board perpendicular to the board. Everybody see that? It's a plane. It's like this plane right here. This is the plane that we're talking about. It's just cutting into the board perpendicular to the board, but its intersection in the xy plane would be the line y equals -x. Okay? So how would we write that? This is the way we could write that in general. If z is any real number, then this is how x and y are always related to z. Okay? So it's infinitely many solutions, but this is how they're constrained. They have to follow that pattern. Okay? That seems you're probably thinking, oh my God, how am I going to? So the way you're going to come up with these solutions, I'm going to give you one on your homework that's like a 2-point bonus that you can, it's not really worth anything to speak of. When I show you how to solve these systems using matrix methods or technology, then you'll have a better way of identifying right away what's going on, right? What is, if it's infinitely many solutions, how are they related? What's the constraint? And there's a really easy way of showing that. This is where technology and matrix approaches are so useful. It makes this way, way easier than doing this algebra. Can you imagine how difficult this problem would have been if let's go back to like that one, or even that one. What if I had a 6x6 system with 6 variables and 6 equations? Okay, that's a load, right? I mean, think about all the algebra that would be required to solve that thing. You would have to find 5 different pairs of 5 equations to eliminate the same variable to get a 5x5 system. You'd have to find, within that, you'd have to find 4 different pairs of equations that eliminate the same variable to get a 4x4 system. Take that one, you'd have to pick, out of that one, you got to pick 3 different pairs of equations that eliminate the same variable to get a 3x3 system, and then solve that one like we did this one. That's a lot of work, right? And then when you solve the 2x2 system, you could just work your way back up through those other systems to find the remaining that would take you a couple hours to do, probably, maybe more, because you're probably not going to get nice integer solutions. You're going to get weird solutions. So the computations are going to get really dense and really ugly, right? So this is where matrix approaches. You can do something like that in 2 minutes. Okay, so that's the next thing I'll show you. Now that's not really a high school topic, but it's something that I wish I would have seen in high school before I went to college, and so I'm going to show it to you guys. And then I'll show you how to do it using technology. Okay? Make sense? So most of the questions on your assignment, the assignment I'm giving you today where you're solving these things algebraically, like for a problem like this one that we just did, you wouldn't have to fill in this part. You would just say, if there's one solution, what's the ordered triple? Or are there infinitely many solutions or no solutions? And you'd be done by just saying infinitely many solutions on this one, right? You would have known that right away because you got 0 equals 0. Okay, that makes sense? Okay. Okay. Well, you know what? I got to be careful with that because that's the way that's often taught, but I don't like that because that's really not true. Just because these two are the same plane, I would still have to make sure that the other two aren't different planes. If I took either of the other two and tried to eliminate a variable, like what if I took the first two and I eliminated a variable and I got a false statement, right? Then that would mean 2 of those planes overlapped, but one of them was parallel and didn't overlap, and there'd be no solutions then, right? That makes sense? So you still have to, if 2 of them are the same, you still have to show that any other pair isn't no solution. You get that? We can see that right away though, can't we? If you look at the top 2 equations, there is no way that that's going to give you, because the middle equation doesn't even have z's. So we can't eliminate the z's even if we tried, right? So no matter what we did in that pair of equations or the bottom 2 pair of equations, I'm never going to get this situation where we get a 0 equals a number or something. Couldn't possibly happen. So we already could tell that for this one, no matter what, we're going to get an answer here, and these are the same plane, and so we guaranteed there's going to be infinitely many solutions. Right? Make sense? Okay. Again, all this gets a lot easier when you use matrix operations, though, which I will show you. Okay. I think that's probably good for today. Yeah. We agree with that? Okay. All right.